with equations of lines. We already started discussing some equations of a line in plane last time on Friday. So today we are going to have let's say, a very quick run through what we read about lines last time, and we will move on and do some practice exercises. So let me put this away. Let me put this away. Okay. Now I'm ready to begin. So there we are. Let me first get my pen ready. White. Yes. It works. Okay. So there we are. What we had last time was, first of all, we started with an equation of a line, understanding that we start with a point that is known, and we have also a vector that actually tells us in which direction this line should be drawn. Whether in 2 dimensions or in 3 dimensions, it doesn't really matter, because the general theory does not actually depend on the dimensionality of vectors. And so we actually found that we had one specific equation of a line, and that was this one. That is, if I know a point and if I know a direction vector, and this is the direction vector, the coordinates are mn in 2 dimensions, then we can write a vector equation in terms of a given point, and a known direction. And then the next thing we looked at was the equation of a line that passes through 2 given points. So the vector is seemingly not given. The direction is seemingly not given. But let's understand that a vector on the line, including, for example, this vector m1, m2, is also a very good direction vector because it does indicate the direction. So we have this second type of equation through 2 given points. Or sometimes we say the point-point equation. Then the next thing we had to consider was the general equation of a line. That is, if we rearrange this first equation, we get something like this. And then we considered n over m, the fraction n over m, and we saw that it actually is the tangent of the angle alpha that the line forms. And, okay, something changed, sorry. I don't know exactly what, but hopefully everything else is correct. All right. And so we had this slope thing. We see that, first of all, we recognize this as the tangent of the angle. We call it the slope. And this is where the traditional equation of a line actually comes from. It's not as if we start with some linear equation for a line. We actually start with understanding what this ratio n over m means, rise over run, as it is written in many countries and in many styles and many textbooks, which actually helps us to find the slope from a direction vector. If we know the coordinates of the direction vector, then the y coordinate divided by the x coordinate will give you the slope. So we have this slope point form, that is, or point slope, point slope. That is, if we know a point and the value of the slope, if we know the slope as a number, then we can write an equation like this. So the number k, the coefficient k, is the slope, also rise over run, also tangent of the angle, also n divided by m. So all these equations are connected among themselves. And finally, the slope-intercept, or the explicit equation, is obtained if we simply open a parenthesis and bring all the constants to the right-hand side. In that case, we get the equation y equals kx plus b, which is our most familiar equation of a straight line, the equation in the function form. This, of course, doesn't work in a certain situation. It doesn't work if we have a vertical line, because then we see that the slope should be infinity. Because for a vertical line, the direction vector, a vertical line, imagine the direction vector is vertical. So the direction vector is actually 0, n, or 0, 1, or 0, anything, whatever you like. The horizontal component of a vertical vector in the coordinates is 0. So in this case, dividing, and remember that we did divide n by n, in this case, dividing is not possible. So for a vertical line, we can say that this equation doesn't work. This equation will not exist for a vertical line, these two, point slope and slope intercept, because the slope is not a finite number. K is not a finite number. We have to divide by 0, which is not possible. So this is, of course, except for vertical lines. The rest can be written for vertical lines, for horizontal lines, for slant lines, but these two, number 3, number 4, cannot be written for vertical lines. These don't exist for vertical lines. For vertical lines...
Miss, how about 1? 1 also, for 1.
What do you mean 1? What do you mean by 1? 1 is a number.
No, 1, the first equation where x minus x0
the first equation,
over n.
yeah. Oh, you think that if m is 0, then you cannot... In fact, okay, I understand what you mean. The problem with equation number 1 is that, you know, that 0 over 0, when we solve, let's say, linear equations, 0x equals 0, we know that x can be anything. This can be anything. Last time I already mentioned, it's indeterminate. It's not determined. You cannot say it's anything specific, but you can say it's anything. 0 over 0 can be fitted together with everything else, which means that in this case, for this first equation to exist, it would mean that x has to be equal to x0. So that we get 0 over 0, right? If m is 0, then to make sense, x must be equal to x0, which actually means a vertical line. This is the equation of a vertical line. Okay. Whatever y is, whatever this second ratio happens to be, for whatever value, we can actually see that if x is x0, we have 0 over 0, the first ratio, it fits with anything. So this means that for any y value, x is equal to x0, and this gives us our vertical line. So this is all technically possible, except for the number 3, number 4. But yes, of course, because there are vectors that have a coordinate equal to 0, horizontal vectors, vertical vectors in this case. Yes, of course, we can define a line even using those vectors. It's just that we cannot get meaningful number 3 and number 4 for them. Okay, and so we call this slope-intercept the explicit equation, or slope-intercept equation, because if x is 0, then y is b from this equation. And as we already saw last time, I got this far, I said, okay, so b is the number on the y-axis through which the line passes. So we can always see a point, one point from this form is always visible, and that is 0b. That is the y-intercept. And then if you understand the slope as rise over run, this was the situation where we can actually sketch a line. If we know the equation in the slope-intercept form, we simply mark the intercept on the y-axis, and then we do the slope like the staircase. Run, rise, to get the points. Okay, now the next attempt. We know that if a line can be defined by the direction vector S, there's another possibility. If we mark the other vector n that is perpendicular to this line, a vector that is perpendicular to this line. Again, if I know a point and if I know a vector perpendicular to this line, I can draw the line in one and only one way. Again, that's a theorem from school geometry, that through a given point, it is possible to draw one and only one line perpendicular to the given line. In other words, if I have given or imagine a line given by the vector n and by the point, the red point, this means I have only one line, only one way to draw this line perpendicular to the vector n. And so how do we find this? How can we find this? We call this vector n the normal vector of the line. You should actually remember this word, normal, because in mathematics, the word normal has several meanings. But the first meaning you have to understand, normal means perpendicular or orthogonal. Perpendicular or orthogonal. So normal vector of the line is a vector perpendicular to that line. We will also see the normal line of a graph later in calculus. We will see the normal vector of a plane in this unit in analytical geometry in 3 dimensions. We will see in the 7th unit the normal vector, the normal line to a surface in 3 dimensions. So normal in our understanding is orthogonal, perpendicular. We will have this, but of course, those of you who will also take statistics, perhaps you remember, those who have had statistics at school, the normal distribution, again, is slightly something different. It doesn't have anything to do with perpendicularity. So normal in mathematics has different meanings, but we shall use the meaning of perpendicularity. And so if the vector MR on the line can of course be written as x minus x0, y minus y0. That's because, as always, we write the vector using the coordinate of the endpoint, which could be changing x, as the point M is, let's say, running across the line, the running point, the current point, or the random point. It's any point on the line. Minus x0, that would be the fixed point, M. And the same with the y coordinates. So the vector MR can be written using these coordinates where, yes, x and y are variables. Then, of course, to have the normal vector perpendicular to this given vector, what we have to do is we have to find the scalar product and say it should be 0, because two vectors are perpendicular if and only if the scalar product is 0. That is, of course, if we are not having a 0 vector. So normal vector n, that is some coordinates a, b, times any vector on the line, mr, must be 0. So if we multiply the coordinates, we get a times x minus x0 plus b times y minus y0. That is the dot product of these vectors. Please remember, it's the dot product. In this case, we are simply checking perpendicularity of two vectors. That is the dot product. Vector n times vector mr, dot product, scalar product, must be equal to 0 because we demand that these vectors are always perpendicular. And so we have a normal vector equation of a line. Normal vector equation of a line. So it looks like this. I'm just repeating the previous and getting rid of the unnecessary writings. So the normal vector equation. So we have to remember that the vector n has coordinates a, b. This means it is a very good equation. This means it's a very good equation. Why? Because when you look at this equation, you immediately know two things. You know the normal vector AB because you look at the numbers and you see A and B, and you know a point on this line, as always. So in this case, we had the direction vector and here we had k, that was the tangent of the angle, but it was also n divided by m of a normal vector, of the direction vector. And here we have the normal vector AB additionally. So when we read this equation, we immediately see one point on this line, that would be x0, y0. And we also see the normal vector, the vector that is perpendicular to this line. And again, if we open these parentheses, if we open the parentheses and combine the numbers, the constants, we get the general equation, ax plus by, and c would be the combination of all the previous constants. That is, C would be A times minus x0 plus B times minus y0. So these numbers combined would give us the constant C. By itself, the constant C does not mean anything. It's simply a combination of other constants. However, we still see vector AB. We still see the normal vector very clearly. The thing to remember in this form is that the constant C does not have a specific geometrical meaning. It is simply a number obtained by combining the other constants. But apart from that, again, you can, for example, choose some value of x to find the corresponding value of y. So from any equation, it is always possible to find as many points on the line as you like. You choose x value, find the corresponding y value. This will always be possible. And finally, the last equation, the seventh equation of a line, that would be intercept, or equation in the segments of axis. So it looks like I have placed, let's say, in a not a very efficient way, I have placed the axis. I will redraw the axis with white so that you see what is going on there. In this case, they are not very visible. So if we have the two axes of the coordinates and the line, if it intersects both axes, so B is the y-intercept. The notation, by the way, will be the same all through analytical geometry. B is the intersection point of the line with the y-axis. Now, if we denote the intersection point of the line with the x-axis, then we get an equation of this line as shown. X divided by A plus y divided by B equals 1. This is the line. This is a line. You can see that it definitely is a line. For example, if you multiply this equation by AB, you would get something in the form 6. If you multiplied both sides of this equation by AB, you would get an equation in the form equation 6. So this is definitely an equation of a line. Now, if we just check A0, so this point has coordinates A0 and the y-intercept has coordinates 0b. If we put A0 into the equation, we get that this point indeed belongs to the line in this equation, this type of equation. If I put 0b in the equation number 7, I still get 1 equals 1. So we see that if I write an equation like this, then indeed it is the equation of the line passing these 2 points on the axis. This is, of course, again, only possible if the line intersects both axes. if the line intersects both axes, that is, if it's not parallel to one or to the other axis. But altogether, yes, if we simply know 2 points on the axis, we can write the equation immediately, whatever those points are. So for practical purposes, why do we have 7? That's something I already mentioned last time. We have 7 different equations of a line for the simple reason that we might have different information given. We might have 2 points. We might have point and a vector parallel or a vector perpendicular to this line. We might be given the slope. We might be given the intercept, the points on the axis. We might have the normal vector already mentioned. So basically, we choose we could call these templates. We choose the template for the equation depending on what information we have. What is the most convenient way of getting an equation of a line? In principle, the preferred form would be the general equation or slope-intercept form of equation number 4 or number 6. However, it's not always strictly necessary to simplify it. And we will have situations where, in fact, maybe some other form is, let's say, better at least to start with. And then we can transform it, simplify it, and get something nicer to look at. These are not all very nice to look at, but we can always simplify things. And so, y-intercept and x-intercept, so the 2 intersection points with the axis. These A and B things will actually, the constants A and B, the intersection point with the x-axis, intersection point with the y-axis, this will actually hold throughout analytical geometry. Later on, when we talk about ellipse, hyperbola, parabola, A and B will still have the same meanings. B will be the point on the x-axis and A will be the point on the, B will be on the y-axis and A will be on the x-axis. This is something that will stay throughout our analytic geometry in the plane. And now, so what we have is these 7 equations one more time without any unnecessary extra writing. So 7 of these. This is still the same. You don't have to copy it all over again. I'm simply putting it on a clean screen. You might even take a screenshot if you like. So all equations in one place. However, of course, you do have everything in the lecture transcript, and it's in Octos, it's online. And now applications. What do we do? Why might we need equations of lines? To graph, maybe, but in general, we basically need, for example, to find the angle between 2 lines. That would be one thing. And so how do we find the angle between 2 lines? Suppose we have 2 lines in the plane, and yes, suppose they intersect. And we need to find the angle. So let's first of all remember that the angle between 2 lines is the smallest angle in the intersection. Not the obtuse angle, but the acute angle. The smaller angle, not the obtuse angle. So in fact, even if we find the angle that is obtuse, we should use the acute angle. The definition of an angle between 2 lines is the smaller of the angle at the intersection one. So we must make sure that it's the acute angle. And we can find the angle, for example, if we have the direction vectors. Could be, for instance, the direction vector for one line, the direction vector for the other line. And basically, if we put these vectors at the same point, we see that, yes, it is the angle between the 2 lines. It doesn't matter what the intersection point is. It doesn't matter what point is mentioned in the equation of the line. What matters only is the 2 direction vectors. the vector, for example, S1 and the direction vector, for instance, S2. However, it might just happen that the two vectors form an acute angle, that the angle that we get is acute. In that case, we need to make a little bit of correction. So we can have the cosine of the angle between two lines. The cosine of this angle between two lines, the angle phi, is, yes, the cosine of the angle between the direction vectors, according to vector algebra. However, if this happens to be negative, if the vector scalar product happens to be negative, then actually I should take the absolute value to make it positive. Why? Because if the scalar product is negative, it means the cosine is negative of the angle. That means it's an obtuse angle. And to get the acute angle, we simply need to take the absolute value. If we take the absolute value of a negative number of the negative cosine, then we get the cosine of the angle on the same line. So the angle, the cosine of this angle would be negative, but the angle of our acute angle would be evidently the opposite positive value of this cosine. That's why we have this absolute value. So in principle, you use these absolute value, the modulus lines, if you get a negative vector product, the scalar product. If you have it positive, then you don't even need to write them. The same goes as the angle between the normal vectors. I will choose different colors, perhaps. Let's take red. Normal vector 1 and normal vector 2. See? Normal vector 1 and normal vector 2. The angle is the same again. The angle between the normal vectors is the same as the angle between the two lines. Because the normal vector is, we could say, the direction vector rotated 90 degrees. And if we rotate both direction vectors 90 degrees, then the angle between them stay the same. Again, the same thing as with the direction vectors. The cosine might happen to be negative. So the vector dot product n1 times n2, the normal vector product, might be negative. Again, that would mean the cosine between the vectors is negative, the angle is obtuse. But we need the corresponding acute angle. That's why we use this absolute value. That's why we must use the absolute value. So if both lines have equations using direction vector, then you use direction vectors. If both lines have normal vectors, you use normal vectors. If one line has direction, the other normal, then you need to change. You need to transform one of the equations so that you get them in the same form. And then you can choose the correct formula. There is another way of finding the angle between lines, and that is if we have the general equation in terms of the slope. By slopes from explicit equations, then the formula is this. Tangent of the angle between the two lines is k1 minus k2. That is, if we have one line, y equals k1x plus b1, and the second line, k2x plus b2. So k1 and k2 are the slopes. In that case, you would see that you can use these slopes, which are tangents of the angles, of course, between the line and the x-axis, to get this. This has a nice, comparatively simple trigonometric explanation, but we will not be going into trigonometry. Just remember that in trigonometry, the angle, if you have one line has angle between it and the horizontal direction, the other line has another angle, then the angle between these two lines is the difference. the difference of the two angles, and the tangent of the difference of two angles is expressed using the tangents of those angles. So this formula actually comes from trigonometry. As for me, it's important that you have this formula, for example, in your formula list, in your notebooks, maybe in your heads, so that if the two lines are given by slopes, that is, if they are given explicitly by the most common equations of them all, then in fact you can find the angle between these two lines. One more time, once again, you have to make sure that you subtract. We are assuming that K1 is greater than K2. So we take the greater slope, subtract the smaller slope to make it positive. If not, you will need to take again the absolute value, because we have the same thing. If the tangent happens to be negative, then we have an obtuse angle, but we need to take the acute angle, the smaller one. So 3 ways of finding the angle between two lines. However, of course, we have special cases. Two lines could have any old angle between them, but they could also be perpendicular, or they could also be parallel. So special cases, 2 special cases. If two lines are parallel, then what can we say? We can check, for example, the direction vectors, but these direction vectors, they do not have to be equal. If they are parallel lines, the direction vectors are collinear. They could be parallel going in the same direction. They could be anti-parallel going in opposite directions. They do not have to have the same length, because it depends on how we write the equation of the line. But in principle, the direction vectors evidently must be collinear. I will choose a lighter pen because otherwise it's still messy. So the direction vector S1 for one line, direction vector S2 for the other line. Of course, the lines are parallel if the direction vectors are collinear. Also, two lines, okay, I forgot the order in which I wrote this. If the two slopes are identical, so if two lines have the same angle with the x-axis, the tangent is the same, and of course the slope has to be the same. So two lines are parallel if they have the same slope, or if they have parallel direction vectors, or if they have parallel normal vectors. So here we would have the two slopes that are equal. Here for these two lines, for example, we might have parallel direction vectors. That would be C. This would be the option C. This would be possibility C. You see, slope, that is the direction vector M1, N1 of the first line is collinear to the direction vector M2, N2 of the second line, which means by the test of collinearity for vectors, it means the coordinates, the numbers M1, N1, M2, N2 must be in proportion. And the same goes for, evidently, in B, for the normal vectors. If I have two lines parallel, supposing these are parallel lines, with the normal vectors, again, should be collinear. Again, not necessarily in the same direction, not necessarily with the same length. It's enough that they are collinear. That is, again, the same test for parallelity. A1, B1, the first normal vector is A1, B1. Okay, that's one and that comma. And the second normal vector would be A2, B2. Of course, again, the coordinates have to be in proportion. So parallelity can be checked by the two normal vectors, by the two direction vectors, by the two slopes. And in principle, I could also say that if I have one line given by normal vector and the other line given by the direction vector, then I could also say that these two vectors should be perpendicular. There's another way of checking. So if one line has normal vector and the other line has direction vector given, then they are parallel if, of course, these two vectors are perpendicular. That's another way of checking. It's just not an official one, because the official ways of checking are using the same elements of the two lines, but we can in fact approach it somewhat differently, taking one direction vector and the other is the normal vector of the second line. That's theoretically, of course, possible. And in practice, if you like, and if you see that situation, if you understand, that might work. One thing, though, I would advise when you deal with vectors and lines in analytical geometry, and further later on also with planes, you should sketch. You should make a simple sketch to understand the mutual position of lines, the mutual position of vectors, so that you can choose the correct approach. Okay, next, two lines and perpendicularity. The perpendicularity would be if the two normal vectors are perpendicular, if the two direction vectors are perpendicular, of course. And finally, something about the slopes. So I will now in fact erase my scribblings and write properly. That is, if the two normal vectors are perpendicular, so if two lines are perpendicular, then their normal vectors, the corresponding normal vectors, should also be perpendicular. And that is, of course, the dot product equals 0. That is, normal vector number 1 times normal vector number 2 must be equal to 0 in this case. The second option, the same goes for the direction vectors, but in fact, the more important part is that the product of slopes must be -1. Now, this is interesting. The product of two slopes must be equal to -1. Only in that case, the two lines will be perpendicular. In other words, if you have one slope, you can find the slope of the perpendicular line. Or if you have both slopes, you can check whether they are perpendicular. We see that the product of the two slopes must be equal to -1. We will, again, in the future, we will use this formula quite a lot. And that will happen in the calculus, in the 5th unit, where we will be checking lines and where we'll be actually looking at the normal line of a curve. But that's in the future. For now, this. All right. Now, let's see. What else can we do with two lines? We can find the coordinates of intersection. So the first application was, yes, we can investigate lines, we can investigate angles, perpendicularity, parallelity of two lines. And now we can find coordinates of intersection. For that purpose, we simply solve the system. XY will be the intersection point as we solve the system. That would be the two numbers, x and y, that fit in the first equation and in the second equation as well. That is from the situation where we had in solving systems and solving linear systems at all. The solution of a linear system is the point whose coordinates satisfy each equation. And in this case, if this is a point that satisfies both equations at the same time, then it belongs to both lines. The linear system, as you remember, so this is something very small. For this, you can change it and use Cramer's rule, you can use Gauss method, you can use inverse matrix method, or you can use school calculations. However, remember that a linear system could have one solution, which means the two lines actually do intersect. It could have no solutions, which would mean the lines are parallel, they don't have common points, and they could have infinitely many solutions, which would mean this is actually one and the same line written with two different equations. And the equations are not always in the normal vector form. You could have any kind of equations for one line, any kind of the equations for the other line, and you could still solve the system and check about the solutions. One, none, or infinitely many. We will in fact apply this a little bit later within a specific task. Our purpose is not exactly finding the coordinates of intersection, because an equation in two coordinates, in two variables, and two equations, a system of two equations, is easy to solve. You did that at school to find the intersection point of two lines. And that's not something we would need to watch very closely and specifically. I'm sure you have actually done that before, and will do that again. One more application, finding the distance from a point to the line. So we suppose we have a point, we suppose we have a line, and we want to find the distance from this point, M, to the line, let's say L. So the one thing to remember is that the distance is the perpendicular distance, the shortest distance or the perpendicular distance. To find this distance, we have two ways. Method A would involve, in fact, finding the distance MP. But finding the distance MP, that would be the length of vector MP. That would be the length of vector MP, the distance from the point to the line, involves, first of all, finding the vector MP. First of all, we need to find the vector MP. So how do we do this? If we know, and I will go now, okay. Supposing we know we have the equation of the line and we have the coordinates of the point. So to find this distance, first of all, we need to find the point P. To find the point P, in order to do everything we need, we first of all need, at least we have to think about it, draw a line through M perpendicular to the line L. So find the equation through the given point perpendicular to the given line. Then you need to find the foot of that perpendicular, that is the intersection point P. That would be find the intersection point of the given line and this perpendicular line. That would be finding coordinates of point P. And then after we have done that, we write down the vector MP or PM and its magnitude. So this is a description of the method. How do we do it actually? How difficult or how easy is it to do? In principle, it's not very horrible, because remember, if you have the line L, you would in general have either its normal vector or its direction vector or its slope. One of these three things is something that we definitely might have. Or, well, maybe if we only have the two intercepts, A and B, we can change this we can change this actually, and we would see the normal vector of that line. So for the line, we have n or s or k, which means if we have the given line's normal vector for the given line, this means from there we can find the direction of the line MP. If we have the direction, it means it will be the normal vector of the line MP. Because if I have two perpendicular lines, what works as the normal vector for one line is actually very good for direction for the other line. If two lines are perpendicular, the normal vector of one line is the same as the direction vector of the other line. So in principle, we already generally will have a vector for this line, MP. And if you have the equation in terms of the slope, then remember for the perpendicular line, you can find the slope as -1 divided by the slope of the first line, because the product of the two slopes must be -1 for perpendicular lines. So this idea of perpendicularity actually is very helpful for finding the distance. Especially, this method is good, especially if we need to find some more specific points on this line MP, some more specific points. In that case, this method works very well. If, on the other hand, the only thing you need to find is the distance, actually, only the distance between the point and the line, then yes, there is a formula. There exists a formula, the method B. Simply a formula, as you can see, we take the normal vector equation of the line, we put in the coordinates of point M in the equation, in the normal equation of that line, and we divide by the magnitude of the normal vector. A squared plus b squared under the radical is the magnitude of the normal vector. In other words, if I have, for example, a line 3x minus 4y plus 7 equals 0, and I have a point, for example, point having coordinates, for instance, -1 and 2, I can find the distance from this formula. In this case, I would say I take this equation of the line. I put the coordinates of the point M into this equation. So that would be 3 times -1 minus 4 times 2 plus 7. All that, if it's negative, I need the modulus the absolute value, divided by the magnitude of the normal vector. The normal vector is 3 minus 4. The normal vector of this line, as you can see, 3 minus 4. So that would be 3 squared plus 4 squared, which means now we have -3 minus 8, that would be -11. -11 plus 7 is -4, but absolute value will make it +4. And here we have 5. So 0.8 units is the distance of point M of this particular point in my example that I invented right now to the line 3x minus 4y plus 7. The distance is 0.8 units. So,
Miss?
Yes.
I have a question. So, Miss, the point P, right? Is it the midpoint of the line?
Line has no middle. Line is endless in both directions. So okay. No, the point P is simply the foot of the perpendicular. See, the base of the perpendicular, that's all. It's not in the middle of anything at all at the moment. The line is, as you know, it goes on infinitely in both directions. So P is simply some point on that line, but it is found as the foot of the perpendicular. We draw the perpendicular towards the line, and that's where we get the point P. The projection, we could say, it's the projection of M on this line. The perpendicular projection.
Okay, thanks, Miss.
Okay. And now some exercises. Now, square root of 5, it's 5. It's 5, it's not square root. All right. Now let's write some equations for some lines. So intersecting the y-axis at this point, so let's imagine what is going on. On the y-axis, at the point 0 minus 2, that would be this one on the y-axis, and angle pi over 4, 45 degrees with the y-axis. With the y-axis, 45 degrees with the y-axis. That's interesting because going in the positive direction, remember that in geometry and in trigonometry, this is the positive direction. From the y-axis, 45 degrees, we actually go there. Pi over 4, 45 degrees. So in fact, the line would go like this. Through the point minus 2 and having this angle 45 degrees with the y-axis. Which means actually the angle with the x-axis, is 3 pi over 4 or 135 degrees. And that means the intersection point means we have the point B, so B is minus 2, the value B is minus 2, that's the y-intercept. And to get the K value, the slope, we have to understand that this is the tangent of the angle 135, and that's minus 1. And so the equation of this line would be minus 1x minus 2. That would be the equation of this line. So I have drawn two lines. The first line was only to show you the angle. The actual line that we are trying to find the equation of is this. This is the actual line that we are finding, the actual equation. So we have to be very careful when reading the task. Sometimes. So I could say sometimes we read this that it's the angle with the x-axis, but in this case it's the y-axis. So the positive angle would be this. If we see that this is the angle with the y-axis. On the other hand, we might say yes, but if we take the angle pi over 4 in the other direction, then actually the angle with the x-axis would also be 45 degrees. And then we would have tangent equal to 1, not minus 1. But in principle, if you have an angle with an axis, in principle, you can find the tangent, you can find the K value. The tangent of the angle with the x-axis gives us the tangent, gives us the slope. And so we can write the slope-intercept equation because the intercept, we can already see, we have the intercept of this line. Now the next one, as simple as possible, parallel to the axis and passing through the point minus 5, 3. Minus 5 on the x-axis, 3 on the y-axis, this is the point P. And we have to write the equations for the two lines that are passing through this point and parallel to the axis. So this is something from school, and I would even say from elementary school. So the horizontal line would be actually y equals 3, or you could say as the general equation y minus 3 equals 0. That would be the horizontal line. And the other one x equals -5 for the vertical line, or you can write x plus 5 equals 0. So as simple approach as possible. Because of course, in principle, if a line is parallel to the y-axis, the direction vector could be written, let's take 0, 1 is the direction vector, 0, 1. We can do it very, very formally. So for the vertical line, no, this was the horizontal line. So for the horizontal line, the direction vector could be, for example, or the direction vector is 1, 0, and the normal vector, which is perhaps easier for the, oh, okay, looks awful, I'm sorry. So for the horizontal line, the normal vector is vertical. For horizontal line, normal vector is vertical. So we could say that the vertical normal vector is 0, 1. There's no need to take anything else. And then if I put the normal vector equation, a times x minus x0, that would be 5, plus b, which is 1 times y minus y0. Then I would have, after simplifying, I do have this very same equation after simplifying. So yes, we may use the normal vector. Just think very carefully what this normal vector would be. Write down the full equation and then simplify it to this form. However, if you can find a simpler way of writing down the equation without going the long route, if you can just see, and if you can just write down the equation of a vertical or a horizontal line, that is much simpler to do, then of course you should do it the simple way. Of course you should do it the simple way. So in principle, yes, it is possible to find the normal vector of this line, to write the equation using the normal vector equation and the point, and then simplify. But as I said, if you can do it in a simpler way, then you should do it in a simpler way. Next, more exercises. Now let's see. Parallel to this line and passing through the given point. So for this line, we actually have the slope -4. If the second line has to be parallel to this first line, then it must have the same slope. Parallel means same slope. Which means we can now write, for example, and we have a point. So we have the slope and we have the point with coordinates x0, y0, right? So we can use the point slope equation. Point slope equation, that was number, I won't say which one, number 3, I think. Point slope y minus y0 equals kx minus x0. Point slope form, so that would be y minus 1, because y0 is 1, equals k, which is -4, times and x minus -1, that makes it +1. And so we have y equals -4x minus 4 plus 1, that's -3. So this is an equation in the same form as the first line. So we simply look at the given equation, we see parallel. Okay, it means we already have the slope. The slope must be the same. We have a point and we have a slope, which means we can use point slope equation. That's actually advisable to do, because with numbers, it's always easier to simplify than to do some other extra calculations if we want to do another form immediately. In principle, we use the template, one of the 7, the one that corresponds to the information we have. We have information slope and we have information point. So we have to use point slope. And that's what we did. And that's what we did. After simplifying, of course, we have a nice equation. Next one, again, parallel and passing through. So if two lines are parallel, remember that I may use the same normal vector. The normal vector, as we see, is 2 minus 5. This is where reading the equation is very important. I look at this equation and say, oh, 2x minus 5y. That means I have the normal vector 2 minus 5. And of course, if two lines are parallel, they can be using just as well. They should be or maybe using the same normal vector. And again, we have a point. So I am using the normal vector equation, that is a times x minus x0 plus b times y minus y0 equals 0. This was the normal vector equation. Okay, so I can write 2 times x minus 7 minus 5 times y minus 2 equals 0. Or if you like to simplify, it's not strictly required because this form looks good enough. It tells me that the normal vector is 2 minus 5, and it tells me that 7, 2 is a point on this line. So I don't need to simplify it because it gives me information, but I can. So 2x minus 5y, and this would be minus 14 plus 10, that's minus 4. So I can take this form, or I can take this general form of equation. So as we see, we use what we have without too much transformation. There's no need to transform the given information into something else. We have these 7 templates, 7 types of equations for a straight line, so we can simply choose the correct template, choose one from our collection, plop numbers into that directly. We just put numbers into the correct form of equation, and then we may simplify it. 2 more. Through 2 points. Now we should use the point-point equation. Let me remind you. X minus x1 over x2 minus x1, y minus y1 over y2 minus y1. So we simply, let's say this is x1 and this is y1 and this will be x2 and this will be y2. And all we have to do is just write this equation using the numbers that are given. So we have x minus negative 2, that means we have plus 2, divided by x2, that is 3, minus negative 2, that is plus 2, and on the other side, y minus y1, that is 4, divided by y2, which is minus 5, minus 4. And after simplifying, x plus 2 over 5 equals y minus 4 over minus 9. So we can say that the direction vector for this is 5 minus 9, for example. So another option is, yes, of course, you can find, first of all, you might find the direction vector as the vector KL. Of course, and then use the first kind of equation. But as it is, whichever it is easier for you to understand and remember the plan of actions. So yes, you could find the S, and then you could use either K or L as the given point on the line. That should not be a problem, whichever you prefer. And yes, of course, if you really want to write it differently, after finding S, you can, remember this is M, and you can, if you want, I am not asking you to do that, but you can take that slope, and the slope was, remember, n over m, that is rise over n, that is minus 9 over 5. So yes, in principle, I could write it in the slope point form or slope intercept form. Of course, I could write it using the slope. It's not strictly required. It's not strictly required. I would say write whatever equation you can, and then if necessary, you can change it. You can change this even by cross multiplication. The cross products, the diagonal products are equal, and simplify from there. So in principle, as soon as you have this one equation with constants in it, with numbers, you can simplify it in whatever form you want. All you have to do is take one template, put in some numbers, all the given numbers, and then simplify however you like. And another one, perpendicular to this line. Perpendicular to this line. That would mean, first of all, the normal vector is 2 minus 1. You could say, for instance, there are several ways of doing this. You could say, for instance, the normal vector of this line will be the direction vector of this new line. The direction vector of this new line. So the normal vector of the given line will be the direction vector of the new line. Okay, I will write eraser. I will write S new. I will write S new. The normal vector of my line, because I need to have, this is my line, 2x minus y minus 1 is 0. Then I have a point somewhere. And I would say I need to write an equation for this line perpendicular to it. I know that the normal vector for the given line is 2 minus 1, this one. And I say, but I can use this normal vector as the direction vector for this new line. So I can have x minus 3, y plus 2, and using the direction now, 2 and minus 1. I can do it like this and then transform. That would be one way. So the normal vector for the given line is the direction for the perpendicular line. You can easily use that. That would be one way of approaching this. Another way of approaching the same thing would be expressing this is y equals 2x minus 1. Change the given equation. Now I say, all right, the k of the new line should be the slope. Remember that the product of the two slopes is minus 1. That means it's minus 1 divided by 2, because remember k1 times k2 had to be equal to minus 1. Minus 1. And so I can find the new slope, and then I can write y minus negative 2 equals minus 1/2. That's minus times x minus 3, and again change this. So you see there are options and possibilities. What you should do is sketch and think which possibility you want to use. Maybe you want to use the normal vector changing to the direction of the new line. Maybe you want to use the rule for the slope. It's up to you which you use. In the end, if you simplify these equations, in the end, you will get the same line, the same equation. All right, now the next, a triangle, a little bit of geometry. After all, we do have analytical geometry, A, B, C. 3 points. So we have 3 minus 1, we have minus 2, 7, and we have 4, 3. And writing equations of lines. So we can see that to write the equation of the line AB, to write the equation of the line AB. We write an equation through 2 points. We write an equation through 2 points, using 2 points. Or if you like, you can write the vector AB or BA as the direction vector. That would be the same, no problem. So let's write the vector AB, which will be the direction vector of this line, is from 3 to -2 is -5, so -1 to 7 is 8. And so I can say that x minus 3 over -5 equals y plus 1 over 8 is one equation, one type of equation for the line AB. Again, do we transform it? Do we not? That's at the moment is not important. In any situation with a test or a homework or examination, I will remember to state very clearly which type of equation I want, so that you can start by writing that equation or writing another equation, then transforming it. That would be up to you. So in principle, an equation of a line through 2 points. An equation of a line through 2 points, that's it. Median line. To find the median line, remember the median of a triangle is the segment connecting a vertex to the midpoint of its opposite side. So in principle, there are again several options. We could, for example, simply find the midpoint of DC. We know how to find the midpoint of a segment, and again do it through 2 points. Or another option is, we already have the vector AB. We could find the vector AC and think vector AD is half of the sum of AB plus AC. So there are possibilities. For me to understand what possibility you are using, if you have a choice, you should write down, you should explain what exactly it is that you are doing. So in this case, so for AD, method 1 should be, for example, point D has coordinates, let's see, -2 plus 4 divided by 2, 7 plus 3 divided by 2. Remember, we had the midpoint, the midpoint coordinates. So in fact, we have 2 divided by 2 is 1, 10 divided by 2 is 5. And so we can use point A and point D, and we have point A is given, point D we just found, so we can again use the equation through 2 points. The second possibility would be vector AB is given, vector AC is from 3 to 4, 1, from -1 to 3 is 4, so 1, 4, and you can write the direction vector. You can have half of AB plus AC, or you can have the full diagonal of that parallelogram. So the direction vector for AD, would be 1/2, or maybe simply the sum of the 2 vectors. Okay, we can write 1/2, but it doesn't matter. We can take the full sum, AB plus AC. And we would have the direction vector, and we would have still 1 point. So there are options. I'm not finishing this task to the very end. You can try different options at home in the end, and then you can check with the solutions. Do we get the exact same thing? And finally, the altitude or the height, AE. The height. Okay, the height, AE, if I have E. This is a right angle. This must be a right angle. So in principle, to write the equation for the line AE, the line AE will be perpendicular to the line BC, which means we need to find the vector BC, And the vector BC will be the normal vector. So the normal vector for the line AE will be the vector BC because it's perpendicular to this line. Because AE must be perpendicular to BC. So in this case, again, you can find the vector BC. You have to understand it can serve as the normal vector of AE. My sketch is not accurate because in the triangle ABC, it just happens that the angle B looks like a right angle. So I am simply assuming that it's not a right angle and I'm sketching this height a little bit differently. Doesn't look very right, it looks slightly obtuse. So my sketch is not accurate, but what we think is if AE has to be perpendicular to BC, then BC can serve, the vector BC can serve as the normal vector for line AE. And of course, the point A, which can be used all the time for AB, for AD, for AE. So the point A as a given point, as a known point on all three lines. So in principle, for AE, we are writing an equation of a line AE that is perpendicular to the vector BC, which will be its normal vector, and passing through, of course, the point A. Normal vector and point in that form. So this is let's say some directions to what you can do for your own practice at home. Acute angle between the lines. All right. So BCD, do I have more? Hopefully not. 3. So acute angle between the lines. In this case, we have the two normal vectors, and that's what we probably should use. The normal vector for the first line is 1 minus 3. The normal vector for the second line is 2. For the magnitudes, the magnitude of the first normal vector is square root of 1 plus 3 squared, that's square root of 10. And the magnitude of the second normal vector is square root 4 plus 16. That is square root of 20. And so the angle or the cosine of this angle would be the scalar product, remember the formula, n1 times n2, divided by the product of the absolute values. So n1 times n2 divided by magnitude and magnitude. And yes, we will use the absolute value, the modulus, because we see that the scalar product 1 times 2 minus 3 times 4 will be negative. That's why I need the absolute value for it. And here we have square root 10, square root 20. So that would be minus 10, absolute value is 10, divided by square root of 200, which would be let's say 10 square roots of 2. So that's 1 over square root of 2. We know that this is the cosine of 45 degrees. We can rewrite it if you like in this form. What you have to remember is that this is exactly the same thing. So we can make a conclusion that the angle between these two lines is 45 degrees. So when we have the angle, when we have the two lines written in the normal vector form, in the general form, general equations, we commonly use the normal vectors because this is the easiest thing to do. These are the easiest vectors to use. The easiest normal vectors. Of course, we can use something else. Let's try for C, for example. All right. For C, I could attempt to use, for instance, the slopes, why not? I can write 2y equals 8x minus 5. So y is 4x minus 2.5. So the first slope is 4. And for the second line, 2y equals 2x plus 1. Y equals x plus 1/2. So the second slope is 1. And so that, just remember that tangent of the angle was the difference of slopes, and I make sure I take the greater slope minus the smaller slope divided by 1 plus the product of slopes, 4 times 1. So I have 3 over 5. And so this means that the angle is arc tangent of 3 over 5. Whatever angle that is, you can approximately evaluate using a calculator. So I'm not saying this is how you must do it. In principle, there's nothing wrong with going the same way as in the first case, because yes, of course, we see the normal vectors. Absolutely. So we can still use the same approach as in the first case. I just wanted to demonstrate how we can use the normal vector or the slope for the tangent of the angle between the two vectors. And here we might think, what are the vectors of direction? So I see that the vector AB, that would be the direction vector of the second line. The direction vector is from -2 to 4 is 6, from 3 to 1 is -2. And for the first, the direction vector X is 2, that is, this is a vertical line. This is a vertical line. So I can say that the first direction is vertical, that is 0, 1. And in fact, I could now use the two direction vectors again. So I can say S1 times S2, 0 times 6 plus 1 times -2. That would be the dot product. Cosine of the angle, the dot product, it will be negative. So yes, I will need the absolute value. And here the length of vector 0, 1. Of course, it's 1. A vertical vector, 1 unit. And the length of the second one, let's see, 36 plus 4, that would be square root of 40 here. And so we see 2 divided by square root of 40. We can simplify it a little bit. 2 root 40 over 40, or actually 4 root 10 divided by 40, so root 10 over 10 is the cosine of the angle. So the arc cosine of this number would be the angle itself. So we can, as you see, I simply wanted the 3 demonstrations. I wanted to show you that we can use the normal vectors, and in many cases, it's the most comfortable and shortest route. In some cases, we may use slopes, especially if even one of the lines is given by the slope equation. Or if we have 2 points, then the first thing we can determine from those 2 points is the direction vector. In this case, the easy route would be use both direction vectors. Next, projection, symmetric projection, distance. Okay, I will do this because we don't have much time remaining. Symmetric, because that involves everything. So I will also find the projection. So we will find also the projection of M. And if you want, we can find also the distance from the point to the line. So we suppose have a point, -2, 4. We have a line 3x plus y minus 8 equals 0. The point that is symmetrical to this one, would be, of on the opposite side at the same direction. Let's call it the point N. That will be the symmetric point, but we don't know its coordinates. If it's symmetrical, we understand this has to be perpendicular and this distance has to be the same. Which means I might not want even to see the distance, but I understand that somehow I need to find that projection of M on the line, perhaps. So what we do, remember the steps. The first step is we need an equation of the line MP, which is perpendicular to our line. So the normal vector of the given line is 3, 1. And we can say we will use the direction for this new line, the same normal vector, 3, 1. Because the normal vector for the given line is the direction for the new line that we want to do. And so the equation of MP, and so the equation of the line MP would be x minus -2 and y minus 4 divided by the coordinates of the direction vector, 3, 1. We can even simplify this equation. But in fact, I would prefer to write this in the parametric form. So x is, remember, if this is the parameter t, then actually I have -2 plus 3t. Remember, x0 plus t times m, y0 plus t times n, which we didn't have probably, but I can rewrite it in this form. If the ratio is t. We will do more with this in 3 dimensions. And y is 4 plus t. And then I can simply use this in the line equation. So that's one way of finding the intersection point. Next time we will start by doing it in a different way. So to find this point, I would say the given line, and this is a system of equations, or even this is an equation for MP. So I have to solve a system. Okay, let's skip this parameter t, because I think it will be probably simpler to solve a simple system. So we take the equation of the given line, and we take the equation we got of the new line. So I will just cross multiply, and I will have x plus 2 times 1 equals 3 times y minus 4. So this is the line L, and this is the line MP. And if I solve this equation, if the system, I will find the coordinates of P. The projection. Because it's the intersection point, of course, of the given line and the perpendicular line. So 3x plus y equals 8, x minus 3y equals those. Minus 12 minus 2 is minus 14. And solving this, for example, 3 times first equation plus the second equation, just like Gauss method, but we are not doing it matrix way just to save time. 9 plus 1, 10x, these will disappear. 24 minus 14 is 10. So x is 1 and y is, if x is 1, then y is 8 minus 3, 5. So the point P has coordinates 1, 5. And if I know the coordinates of P, 1, 5, I can, in principle, find the distance from M to P. And I can find the point N. How do I find the point N? By simply understanding that P now is the midpoint of MN, of the segment MN. That is, I can find the coordinates of N using the coordinates of M and of P. So that would be 1, that is x of midpoint, equals -2 plus x of n divided by 2, which means x will be what? 4. And the second coordinate, 5 of P, equals the y coordinate 4 of M plus y of n divided by 2, which means y is 6. So in principle, now I already see that n has coordinates 4 and 6. N has coordinates 4 and 6. Using the idea that the midpoint is known and one of the ends is known. From the idea of midpoint. For that purpose, evidently, we needed to find this point. And yes, of course, we can find the distance. The problem with distance is the distance from formula will not help us to find n. We can find the distance from M to P, but using the formula will be not very helpful. So in principle, we use the formula of distance in very, very rare occasions. Because in principle, usually we need not so much the distance itself as the construction, perhaps the perpendicular line, the projection of the point on the given line, and in this case, the point that is symmetrical to the point M with respect to the line. So perpendicularity, how to write an equation of a perpendicular line, how to use the midpoint to find the symmetrical point, all these things. Now let me check a little bit. So projection, this would be exactly the same thing, finding the projection. That was, I will just remind you of the plan. So we have the normal vector. We have the normal vector from this line. For that other line, it will become the vector, the direction vector for the new line. Then we have point and we have the direction vector. We write the equation for this new line. P, I will call this F, because it's also called the foot of the perpendicular. And that will be the equation for the line PF. And finally, the intersection, finding the system. The intersection of PF and the given line, let's say L. And that will be the projection of the point, because by projection, of course, we understand the perpendicular projection, the orthogonal projection, the foot of the perpendicular. And in the last case, that will be exactly the same thing, except that if you write an equation for this line, you will get M1, M2 as the direction vector, not the normal vector. So the direction vector for this line will be normal vector for the other line. A slightly different approach. So we will have the direction vector of this line. So if I want to find this other line from point P, perpendicular to the given line, we will see that the normal vector is the direction vector of the given line. And again, the rest goes as previously. As soon as we write the equation for the perpendicular line, then we can solve a system, equations of both lines, to find the intersection point in exactly the same way. All right, the answers are in the lecture file. Next time on Tuesday, remember we only exchanged elementary mathematics and regular maths last week because of the quiz, because of the unit test. So next time on Wednesday, we have the lecture at 8:15, the normal time as always, and we will start looking at conic sections, second order curves like circle and ellipse. That's next time.
Miss, when will the results of the Unit 2 test will be posted?
When I have finished marking them, I have about 60 of you and I have 90 other students. So I have to do things in order. Probably within this week.
Okay.
I don't want to leave it for the next week, but definitely not today, not tomorrow, and most probably not Wednesday yet.
Okay, sure, Miss. Thanks.
All right, I will see you on Wednesday then.
Miss, the homework assignment. Why the first assignment will it be marked as well, right? So
it will be marked when I have time for that. As I said, 60 plus 90, 150 people. How many assignments? When I do it, I will post it, of course.
Sure, Miss. Thanks.
All right, goodbye.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.